Have you ever wondered if our entire universe is nothing more than a delicate illusion, one that could vanish instantly, without warning? What if the greatest weakness in the cosmos isn't lurking in distant black holes or the edge of space, but right here, hiding in plain sight down at the quantum level? Today, you're about to uncover a terrifying truth. Scientists have discovered a flaw so fundamental, it could unravel reality itself in a microsecond, leaving absolutely nothing in its wake. It's not science fiction. In fact, this cosmic danger was first revealed by one of the most legendary minds in physics, Sidney Coleman, whose groundbreaking insight in the late 1970 seconds shocked even his closest colleagues. What he found was chilling: the possibility that the universe is sitting atop a trap, a false vacuum, vulnerable to catastrophic collapse at any moment. Imagine, at any point in space and time, a change could begin that's so final, so unforgiving, not even atoms or stars would survive. How did Coleman and his peers uncover this existential threat? What led them from playful chalkboard equations at Harvard to the realization that everything: life, matter, time, could disappear in an instant? Throughout this documentary, you'll journey deep into the standard model of physics, meet the great pioneers who shaped our understanding of reality, and face the stunning conclusion: the God particle is not just a key to mass, it might also be the destroyer of worlds. Not only God knows, I know. And by the end of the semester, you will know. This is how the physicist Sidney Coleman would kick off his lectures on quantum theory at Harvard. Coleman claimed that he never really liked teaching, but his enthusiasm was electric, and his courses were considered legendary. Though his name is not as well known as Einstein or Hawking, he was held in the highest regard amongst his peers. Indeed, groundbreaking physicist Sheldon Glashow once said, "He's kind of a major god. He is the physicist's physicist." And yet, arguably, this jovial legend of physics's greatest achievement was revealing something truly spine-chilling. For in the late 1970 seconds, Coleman figured out how to destroy the entire universe. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. However, one could always draw stoic comfort from the possibility that perhaps in the course of time the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. Coleman discovered that our universe is under constant threat. At any moment, at any point in time and space, reality could begin to change. Change in a way so unforgiving that nothing could survive it. The story of the unraveling of this mystery will introduce us to some of science's greatest personalities, men and women who peeled back reality and created a framework out of which our universe could appear. Most importantly, this story will pull us deep into the bizarre world of the standard model of particle physics and the one particle that sits apart from all the others. The particle with the power to eliminate everything in existence, that goddamn particle, or, as it's more commonly known, the God particle. The Soviet lunar rovers explored the moon in the 1970 seconds, remotely driven from mission control in Crimea. Operators viewed live TV images sent from the lunar surface and radioed commands back via their landers. A true feat of engineering for the time. Indeed, it wouldn't be until 1997 that another remote control vehicle would land off-world. Sometimes, it's useful to be able to control something remotely, even from the other side of the world. As the Trinity test mushroom cloud bloomed into the sky on July 16, 1945, physicist Kenneth Bainbridge turned to Robert Oppenheimer and uttered the immortal phrase, "Now we're all sons of bitches." After the magnitude of the test had set in, and the initial flurry of excitement had dulled, there was a palpable sense of unease across Los Alamos. In the adrenaline rush after the detonation, famed New York physicist Richard Feynman had played his iconic bongos on the hood of a Jeep. And, in his words, everyone had parties. But quickly, the mood turned sour. I sat in a restaurant in New York, and I looked out at the buildings, and I began to think about how much the radius of the Hiroshima bomb damage was, and so forth. And I would go along and see people building a bridge, or they'd be making a new road, and I thought, they're crazy. They just don't understand. Why are they making new things? It's so useless. The Manhattan Project had employed over 130,000 people in its prime, and 26 of its scientists already had or would go on to win a Nobel Prize. After this long interruption, it was decided that physicists should gather together to return to science for science's sake once again. In 1947, Oppenheimer himself helped organize a conference on Shelter Island. To quote later Nobel Prize winner Julian Schwinger, it was the first time that people who had all this physics pent up in them for 5 years could talk to each other without somebody peering over their shoulders and saying, "Is this cleared?" It would be at this conference that Richard Feynman and Julian Schwinger himself would propose some groundbreaking quantum ideas. But what does any of this have to do with Sidney Coleman and the destruction of the entire universe? To answer this question, we must take a journey downwards, down into the deepest layers of reality, below the scales of molecules and atoms, beyond the pieces of the atomic nucleus, down to what we think are the ultimate building blocks of reality. To a physicist, this world is written in the language of the Standard Model of particle physics. The Standard Model is the result of more than a century of deciphering the laws of the universe, a world even more fundamental than the atomic one explored by the Manhattan Project. First, there are the fermions, the fundamental particles that comprise the stuff of matter named after Italian-American physicist Enrico Fermi. Fermions come in two types: the quarks and the leptons that feel the fundamental forces differently. The quarks feel the strong force and are bound together by it into composite particles, collections of 2 or 3, including the protons and neutrons that sit at the core of every one of your atoms. Atoms are circled by electrons, which, as leptons, completely ignore the strong force. Complementing the fermions are the bosons, named after Indian physicist Satyendra Nath Bose. The bosons are different as they carry the fundamental forces between the fermions. For the strong force we met a moment ago, the carrier of force is the gluon. For electromagnetism, the boson is the photon, the particle of light. For the weak force, there are the W and Z bosons. And for the final fundamental force, gravity, physicists still aren't sure. Now, the idea of bosons as force carriers may seem strange, but you have to remember that particles are not really particles, and this is key. The Standard Model is written in the language of quantum mechanics, where everything is a wave in a field. An electron is a ripple in the electron quantum field. A quark is a ripple in a quark quantum field. And each boson is a ripple in a boson field. Everything is fields. In the simplest form, a field is something that is spread throughout space, and that something attaches a number to each point in that space. For example, think about the temperature in the air around you. Some spots may be warmer, some cooler, and at each point, the temperature is represented by a single number, a simple scalar field. Other types of fields are more complex but still familiar, like electric and magnetic fields. At each point in space, these fields have a number and, importantly, a direction, a vector at each point in space, so it's no surprise that these are known as vector fields. These and many more complex fields are what many aspects of physics are built from, in particular, a type of field called a quantum field. And to explore how these work, let's talk about the electron. The electron quantum field fills all of space, encoding the properties of what makes up an electron at every point. A single ripple in the field corresponds to a single electron traveling through a region. Multiple ripples would represent multiple electrons all encoded in the field. When the field is 0, there are no electrons in that region. The electron field is joined by fields for the other leptons, the muon and the tau and their associated neutrinos. There are also fields for each of the quarks and for each of the force-carrying bosons. There is a quantum field for each type of fundamental particle. All around us, At every point sit all of these quantum fields. But there's more to quantum fields than simply existing. The real power in quantum fields is how they interact. Understanding how this interaction takes place was one of the most important insights in all of physics. And it's here we return to Shelter Island and Richard Feynman. As part of his PhD, Feynman realized he could bring a mathematical shortcut to quantum calculations. Let's look at what happens when two electrons with their negative charge approach each other. It's important to remember that the two electrons are ripples in the electron quantum field. So, they are not feeling each other's presence through their individual electric and magnetic fields. Instead, the presence of the two electrons in the electron field generates a new ripple, this time in the photon quantum field, because the photon is the boson of the electromagnetic force. This photon ripple travels from one electron to the other, and in doing so, it transfers energy and momentum from one electron to the other. This transfer is precisely why the photon is known as a force particle. And when you look at a lonely star on a dark, dark night, the absorption of a photon on the retina in your eye receives energy and momentum from that star. Energy and momentum released by an electron in its distant atmosphere. At the Shelter Island Conference, physicists were coming to grips with this quantum picture of electrons and photons. Julian Schwinger, with his crisp and refined New York accent, lectured first. He was followed by Feynman, who made his way to the blackboard armed with his famous Feynman diagrams, which offered shortcuts to Schwinger's mathematics. Other physicists were initially confused, but in the long run, Feynman's ideas won out, and he shared the Nobel Prize with Schwinger in 1965 for their insights into how quantum fields interact, with Japanese physicist Shinichiro Tomonaga also grabbing 1/3 of the prize. He had delved into the nature of quantum fields, isolated in war-torn 1942 Japan, on the other side of the conflict to Feynman and the Manhattan Project. By the time of Feynman's Nobel Prize win, the Standard Model was growing in success. There were still theoretical holes needing to be patched, but things seemed to be fitting together nicely. All forces should be written in the same quantum language, with bosons transmitting forces between fermions all requiring the presence of quantum fields to carry the particles with particular numbers, the charges of the force, dictating the strength of the interaction. Except a major mystery remained, a mystery that had the potential to tear it all down. For within the Standard Model, all of the fundamental particles seemed to have absolutely no mass. The particle of light, the photon, appeared to be massless, that was true. But not the other particles, clearly not even the electron. So, to understand this mystery, we have to talk about one more fundamental force, the weak force. The existence of quantum fields demanded that there was the equivalent of electric charge for the other forces as well. The strong force, for example, had 3 types of color charge: red, green, and blue charges that determine how gluons are exchanged and how strongly the strong force operates. But in our story, it would be the charge of the weak force playing a pivotal role. The weak force is weaker than both the strong force and electromagnetism, but it is still stronger than gravity. Unlike the other forces, the weak force can flip the identities of quarks and leptons through the exchange of bosons, making it responsible for certain types of radioactivity. With Feynman's view of quantum interactions and the need for bosons to transmit forces, physicists needed a boson to transmit the weak force's influence. One complication: the weak force has 3 bosons that can be exchanged: the Z0, the W+, and the W-. The plus and minus signify the W boson carries its own electric charge. And unlike the photons and gluons, which are massless, the W and Z bosons are massive, each about 80 times as massive as a proton or neutron. This immense mass severely limits the influence of the weak force. While massless particles mean electromagnetism and the strong force have infinite range, the W and Z bosons' mass ensures the weak force can only operate over extremely small distances. This A result of Heisenberg's uncertainty principle limits the energy that can be borrowed from the vacuum, and thus the time and distance the boson can exist before it decays into other particles. So, we have said the weak force is important, and its force boson's massive, but where does this mass come from? What does it have to do with the possible end of the universe? It's time to dive even deeper into fundamental physics, and to do that, we need to find a man who does not want to be found. Dr. Higgs, the J.D. Salinger of physics had already let it be known that he would not be available in any form on Tuesday. On the morning of October 8th, 2013, the world awaited the announcement of the Nobel Prize in Physics. Peter Higgs, however, wanted no part of the expected media frenzy. Instead of staying at home to receive the expected calls and interviews, he quietly slipped away to a local pub. But as the hours ticked by, the media outside built to a frenzy, and Higgs could not hide forever. He headed out, only to bump into an old neighbor who immediately congratulated him. "What news?" Higgs asked. But there could be no doubting what news the Nobel awaited him in Stockholm. But why had he been selected for this coveted prize, one received by Feynman all those years before? To understand that, we return to another Nobel ceremony, one perched between Higgs in 2013 and Feynman in 1965. Nobel Award ceremonies have always been flashy affairs with pomp and regimented protocol. In 1979, with the royal family of Sweden presiding, all the men dressed in black suits and white ties, well, almost all. One man, in distinctly different clothing and a turban, stood out. Abdus Salam, only the second Nobel Prize winner from a Muslim country, unlike Egypt's Anwar Sadat, who had collected the Peace Prize the previous year. Salam was in Stockholm to receive the Nobel Prize in Physics, and his choice of dress reflected his pride in his religion and cultural origin. He was not alone. Sheldon Glashow and Steven Weinberg would be sharing 1/3 of the prize each, all there for the same reason. These three physicists delved into the similarities between electromagnetism and the weak force today known as electroweak theory. This unification laid the groundwork for understanding the origin of mass. But before we explore electroweak theory and its consequences, we must remember that electromagnetism itself used to be two separate things. Electricity and magnetism were once considered distinct. In the late 19th century, Scotsman James Clerk Maxwell wrote the equations that unified them, following work by Michael Faraday. He noticed a symmetry, one field birthing another in elegant reciprocity, and added a single term to make the equations whole, unleashing light. Light, he realized, wasn't separate either, simply a wave of the unified electromagnetic field rippling through space. This was the first great unification in physics not born of speculation, but of mathematics, compelled by beauty and truth. If electricity and magnetism could be shown as two facets of one theory, maybe other disparate aspects of physics could be unified. The race for a unified theory was on. The first clue was that some bosons of the weak force carried electromagnetic charge, allowing them to interact with the photon quantum field. This gave Glashow, Weinberg, and Salam the key to the next unification: electromagnetism and the weak force. To understand how electroweak theory unites the two, we need to look at gauge theories. A gauge theory, named for the measuring tool, gauge, is about setting a local reference at every point on a map. Shifting those references changes the description, not the underlying landscape. Gauge theories reveal laws of nature that stay constant no matter how you adjust your point of view. Symmetries in physics indicate hidden structures in the universe. Let's consider a simple gauge field, a value, a direction between 0 and 360 degrees at every point. Crucially, every single one of these vectors has exactly the same length. If your laws of physics only care about length, not direction, you have a gauge symmetry. Rotate every vector, and the physics remains unchanged from this abstract idea. Forces emerge. Quantum fields are built of complex numbers, with the modulus, the sum of the squares, at each point being important. This corresponds to the probability of finding a particle at a particular location. You can rotate these numbers as before, meaning quantum fields have gauge symmetry. Change the field, and the physics is unchanged. The focus on symmetry owes much to Emmy Noether, who saw that hidden symmetries reveal deep truths about physical law conservation of energy. For example, arises from symmetry in time. Her insight was profound. Shift in time, energy remains. Step to the side, momentum is preserved. Symmetry became the engine room of the cosmos. The U1, symmetry, is the mathematical foundation of the electromagnetic force related to phase in the electron quantum field. The conserved quantity, electric charge. However, U1 was too simple for the weak force. Glashow, Weinberg, and Salam realized that two additional numbers, weak isospin and weak hypercharge, were needed, described by a more complex group, SU2. This describes rotations in a more abstract space, where every point is a possible state of a quantum particle. Combining U1 electromagnetism and SU12 weak force, the Nobel winners proved these seemingly distinct phenomena are two sides of the same coin. The mathematics predicted four bosons, B, W1, W2, and W3. Problem solved? Not kite. Steven Weinberg said, one of the consequences of electroweak symmetry is that if nothing new was added to the theory, all elementary particles, including electrons and quarks, would be massless, which of course they're not. The answer lingered in the fizzing chaos of the Big Bang. Right after the universe was born, it was extremely hot. All particles zipped around at almost light speed. Any particle's mass meant little compared to its energy of motion effectively. A massless state, like a photon. In the earliest instant, one electroweak force operated no distinct electromagnetic or weak forces. As the universe expanded and cooled, something must have happened to split them, to give mass to the weak force's bosons. That something was symmetry breaking. In 1964, Peter Higgs and others proposed a radical idea: the addition of another quantum field, a new field characterized by a single value at every point, a scalar field. Unlike other quantum fields, the Higgs field had unique properties. In the early universe, all quantum fields buzzed with energy, but as the cosmos cooled, their buzz faded. For the Higgs field, however, the buzz never vanished. It got hung up, possessing a non-zero value everywhere. To explain this, think of a pendulum, full of energy. It swings wildly. As energy drains, the swings shrink until the pendulum hangs still. Most quantum fields behave this way. After the early universe, their value falls to zero everywhere. But for the Higgs field, it's like a pencil balanced on its tip. At first, perfectly balanced, zero everywhere. Then suddenly, as energy falls, the pencil topples, finally resting with a non-zero value everywhere. The symmetry is broken. The result: the bosons from B, W1, W2, and W3 mix and produce four new bosons. One remains massless, the photon, while the W+, W, and Z0 bosons gain mass, birthing the weak force. What about the masses of other fundamental particles? That depends on how strongly they interact with the Higgs field. But what is mass? You might think it's just the amount of stuff or the thing producing gravity. But more precisely, according to Newton, it's the property connecting force and acceleration resistance to being pushed. That's inertial mass. And it's the Higgs field that gives particles their inertial mass, effectively making space sticky. Massless particles like photons glide through. Others, like electrons, feel drag from the Higgs field. But here's the twist. The mass of fundamental particles, the electron, the up and down quarks, making up the proton, is very small. So where does the rest of the mass come from? Inside each proton and neutron, there's more than just those three quarks. There's a swirl of gluons, exchanged constantly. popping in and out of existence as quark-antiquark pairs. Gluons themselves are massless, but carry energy and momentum thanks to Einstein's E equals mc circumflex 2. That swirl of energy is mass. Most of the mass of atoms comes from this dynamic whirlwind. So, at a thousandth of a billionth of a second after the Big Bang, the universe's temperature was 1,000,000,000,000 Kelvin. A defining symmetry broke, and the cosmos was imbued with mass. But what does this have to do with the destruction of the universe? To find out, we have to weigh the source of mass, the Higgs itself. Sidney Coleman was a brilliant teacher and a piercing critic among theoretical physicists. After his passing in 2007, it took 5 years before other physicists began answering his mystery with the most powerful experiment ever performed. In the late 1970 seconds, Coleman revisited the symmetry breaking that set the Higgs field buzzing and posed a crucial question. Why does the Higgs field buzz with its particular energy? Why didn't it settle on a different energy as the universe cooled? Peter Higgs and others had assumed the Higgs field's energy in their mathematics, but Coleman realized, with small mathematical tweaks, things could change. The Higgs field might settle into more than one possible energy, a game of chance. The path the Higgs field tumbled from symmetry seemed random. Here's what's disturbing. After the universe's birth, the Higgs field's energy may not have dropped to the lowest possible minimum, but could be stuck in a false vacuum, a local minimum. Quantum mechanics, unlike Newton's classical world, allows for escape via quantum tunneling. It's like a ball stuck in a shallow valley that, thanks to quantum weirdness, might suddenly find itself rolling down to a deeper, truer minimum. If the Higgs field is stuck in a false vacuum, it could, at any time, quantum tunnel to a lower energy triggered at a single spot in the universe, with a bubble expanding outward at near the speed of light, annihilating everything in its path. Not even the fundamental laws would remain unscathed inside this bubble. All would be transformed, possibly no atoms, stars, or even space and time as we know them. Should we be worried? Are we living in a false vacuum? Or are we safe, perched at the true minimum? Physicists don't have the final answer yet, but a powerful recent experiment has given us clues. Nestled in the coal mining valleys of South Wales, Lynn Evans grew up with a passion for science. At CERN, on the Swiss-French border, Evans led construction of the largest, most powerful accelerator ever built, the Large Hadron Collider, LHC. The LHC's mission: smash protons together at nearly light speed, unlocking the secrets of matter. In 2012, physicists working at CERN discovered the long-sought Higgs boson itself, finally confirming the theory's last missing piece. But this victory was not without consequence. Measurements of the Higgs boson's mass and self-coupling tell us we're dangerously close to the boundary between stability and disaster. Some calculations suggest we are, indeed, living in a metastable state of false vacuum. So as you gaze at the stars, know this: the universe's greatest weakness could be right beneath your feet, baked into the very fabric of reality itself, and the fate of all that exists may depend on an invisible quantum coin toss made at the dawn of time. Everything you have heard is grounded in the most rigorous science, the unfiltered pursuit of truth, and an unflinching willingness to ask the most audacious questions imaginable. You now know the universe's greatest weakness. Would you dare to find out what happens next? You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.